If you hand the most advanced artificial intelligence on Earth a map of just 50 cities and ask it to find the absolute fastest route to visit them all, its digital brain will completely freeze. To check every single possible combination and guarantee the perfect answer, that multi-billion-dollar classical supercomputer would have to crunch numbers for longer than the remaining lifespan of our entire universe. This is a terrifying mathematical reality that the tech industry desperately tries to hide behind flashy software updates and conversational chatbots. Modern artificial intelligence is running on borrowed time because it has reached a hard physical boundary known as the optimization wall. We are trying to build human-level automated minds using a mathematical foundation that was designed for basic calculators. If we do not completely change how computers explore choices, the grand promise of artificial general intelligence will collapse under the weight of its own bad math. To understand why this happens, you have to look at the multi-dimensional landscape where an AI learns. Computer scientists map out an AI's options like a vast, endless mountain range full of towering peaks and deep, pitch-black valleys. The peaks represent massive logical errors, while the lowest, absolute deepest valley represents the flawless, perfect answer. Traditional computer chips are completely blind in this landscape. They have to crawl through these mountains like an ant, checking every single path step by step, one choice at a time. If the system hits a false valley, which mathematicians call a local minimum, it gets trapped in a shallow ditch miles away from the true destination. This mathematical trap is the exact reason why modern AI models suddenly hallucinate fake facts, confidently make up historical events, or completely break down when solving basic logical puzzles. Tech companies have been trying to overpower this bad math by simply building bigger, hotter data centers. But a quiet, mind-bending revolution just changed the rules of reality forever. Quantum computers didn't just bypass this silicon ceiling. They completely solved the absolute biggest math problem holding back artificial intelligence. And from this point onward, nothing will ever be the same. Before we break down the mind-bending physics that makes this historic leap possible, if you want to understand the pure science driving the future without the sensationalized marketing fluff, hit that subscribe button right now. We strip away the corporate tech hype to give you the real data in plain English, so joining our community is the absolute best way to keep your feet ahead of the curve. Drop a comment down below right now. Do you think we are ready for an artificial intelligence that can think through solutions instantly, or does this speed terrify you? Let's dive straight into the mechanics. To truly understand how a quantum computer shatters this mathematical roadblock, you have to look at how different its core mechanics are from traditional computer processors. A standard silicon chip operates on binary bits, which are like simple household light switches that can only ever be strictly turned on as a 1 or turned off as a 0. Because of this, a classical supercomputer trying to navigate that vast mathematical mountain range has to physically travel down a hill, realize it hit a dead end, travel all the way back up, and try the next path. This linear processing creates an exponential collapse when problems get complex. Quantum computing changes the entire playing field by utilizing a principle called superposition. Instead of regular bits, quantum systems use qubits. Think of a standard bit like a coin lying flat on a table, clearly showing either heads or tails. A qubit is like that exact same coin spinning wildly through the air. Until it lands, it exists as a fluid blur of both heads and tails at the exact same time. This means a quantum processor does not look at paths one by one. It evaluates an entire mathematical landscape all at once. But simply looking at every path simultaneously is only half the magic. If a computer just looked at all answers at once, it would still get overwhelmed by a wave of random digital noise. To solve this, quantum algorithms use a mechanism called wave interference. Think of it like noise-canceling headphones. When a quantum system processes information, the wrong mathematical paths create destructive interference, meaning their waves clash and physically cancel each other out. Meanwhile, the correct optimal paths create constructive interference, meaning their waves stack up, amplify, and grow brighter. The computer does not crawl up and down the mountains. It applies a quantum wave across the entire range, instantly flattening the false valleys and leaving only the absolute fastest route to the perfect answer exposed. This is not some distant science fiction hypothesis. We have officially reached the era of practical verification, and the real-world milestones are dropping faster than the tech industry can keep up. Look at what happened when Google Quantum AI unveiled its state-of-the-art quantum processor called Willow. For nearly 30 years, the entire field of quantum computing has been plagued by a massive engineering obstacle known as error correction. Qubits are incredibly fragile, and even the tiniest shift in room temperature can cause them to lose their quantum state and ruin a calculation. But the Willow chip achieved a historic breakthrough by executing quantum error correction below the critical threshold. This means that as engineers add more physical qubits to the chip, the system's overall error rate drops exponentially, making the calculations more robust instead of more unstable. To show the raw power of this milestone, Google used Willow to run a highly complex benchmark calculation. The quantum chip finished the entire task in less than 5 minutes. To run that exact same calculation on one of today's fastest classical supercomputers would take 10 septillion years. That is a span of time that is literally vastly older than the age of our entire universe. While Google is mastering error correction with superconducting circuits, Microsoft has taken a completely different, high-stakes path to lead the quantum race. They recently introduced their Majorana 1 platform, which is the world's very first quantum architecture driven by a topoconductor. Instead of trying to fix errors after they happen, Microsoft engineered a material stack using indium arsenide and aluminum nanowires to create a completely new state of matter. This structure supports the control of subatomic Majorana particles, which form topological qubits. These topological qubits are protected by an inherent physical shield, meaning they are naturally resistant to external noise and random disturbances at the hardware level. Microsoft quickly followed this up by launching their advanced Majorana 2 processor, swapping out aluminum for lead to drastically increase qubit stability and lifetime. This architectural breakthrough allows for massive scalability, clearing a straight path to packing over 1 million highly reliable, digitally controlled qubits onto a single palm-sized chip. The competition between these tech titans proves that the battle for quantum utility is officially over. The hardware is real, and it is ready to scale. So what does this fundamental shift actually change for the world tomorrow? It completely alters the trajectory of human innovation by transforming impossible math into instantaneous engineering. Take global logistics and supply chain optimization. Trying to find the absolute most efficient route for thousands of ships, planes, and delivery trucks across a shifting global network involves an astronomical number of variables. A classical computer running a standard AI model has to make massive compromises and approximations because it simply lacks the capacity to process that level of complexity without crashing. A quantum system can untangle that entire web in minutes, saving billions of dollars in energy and cutting global carbon emissions overnight. But the impact on chemistry, medicine, and materials science is where the world changes completely. To design a new life-saving drug or an advanced battery material, scientists currently have to rely on slow, expensive, trial-and-error laboratory experiments because classical supercomputers cannot simulate the exact quantum behaviors of interacting electrons within molecules. Quantum computing removes the guesswork. It allows us to model complex proteins with absolute atomic precision, accelerating 250 years of traditional scientific discovery into the next 25 years. We are living through the exact moment when the limits of human capability are being permanently redrawn. The math has officially changed, moving us away from slow, brute force calculations into an era of instant, multivariable clarity. The institutions, researchers, and creators who understand this shift today are the ones who will shape the future of our digital world. Don't get left behind as the rules of computing are rewritten. Make sure you are subscribed to the channel so you never miss a deep dive into the technology shaping our tomorrow, and I will see you in the next one.